As we continue, let's talk about, as we're talking about continuity, let's talk about if we just have a function, how can we figure out where is it continuous or where is it discontinuous? So let's talk about different types, and a lot of these you're already going to know. Maybe you hadn't thought about where is it continuous, but you're at least going to be familiar with these functions. So polynomials, so any f of x equals a sub n x to the n. So the exponents here are integers, positive integers. And so these are always smooth graphs. So just any example. So think about a quadratic, cubic. Quadratic, of course, looks something like that. Cubic maybe looks like that. This would be a quartic, degree 4 polynomial, but they're always continuous everywhere. So all x. Where is it continuous? All x. So if you see a polynomial and you're asked where is this continuous, it's always all real numbers. What about rational functions? So rational functions. So here we have f of x equals p of x over q of x. So p of x and q of x are both polynomials. Where is it continuous? So if you ever see one of these, where is it continuous? You set the denominator as not equal to 0 and solve for x. So any x that you find here, that is where, well, if you say not equal to 0, any x that you find would satisfy that. So, but typically, for instance, if you have x plus 3 over x minus 2, say, you'd say x minus 2 is not equal to 0, so where is it continuous? Everywhere except 2. So as long as x is not equal to 2, it's going to be continuous. And then the graphs, not saying for this one in particular, but we will use 2 here. So we'll say something like that. All right, what about next type? Let's say root functions. So f of x equals square root, and you can have anything under here. We'll just write ax plus b, but you can have whatever under here. Now, when you take a square root, if we're only speaking in terms of real numbers, you can only take the square root of a positive number. So whatever this it is under the square root, that has to be greater than or equal to 0. So a has to be greater than or equal to 0. Just the basic square root function looks like this. Of course, depending on this, we're going to move it around to change the shape and that kind of thing. But when you're just finding these, where is this continuous? Whatever that is has to be greater than or equal to 0. And then let's talk about exponentials. So 2 more exponentials. So f of x equals a to the x. Of course, we can have more than just x. We could have a linear function up there. We could have a rational function up there. But if we're just talking about the basic exponential function, this would be all x. Now, if it's something else like a to the square root of x, then you have to consider, so now this is a root function, so now you have to consider where is this function continuous. So that changes it. So in this case, it would be x greater than or equal to 0. So if it's just basic, or this is a polynomial, all x. If it's something else, then you also have to consider that. But generally speaking, an exponential function, all real numbers. And of course, this looks something like that. Then last one, we'll consider logarithmic function. So f of x equals log base a of x. A is greater than 0. A is not equal to 1. And so this one is greater than 0. And so that function looks like that. Again, if you have something more complex, so you have, some polynomial over here, then x squared plus 2x has to be, actually, this is not equal, so just greater than. That was my mistake, just greater than. So whatever you have in the parentheses here that you're taking the log of, that needs to be, that expression needs to be greater than 0. So whatever you have in here has to be greater than 0. Okay, so certainly need to memorize those in order to do these problems up here, down here. So find all values of x equals a where the function f of x equals square root of 5x plus 3 is discontinuous. So essentially, where is it discontinuous? That means that this is going to be less than 0. So less than 0, so 5x is less than negative 3, so x is less than negative 3/5. Now that's actually, none of that will be in the domain. So that means it is discontinuous at x equals negative 3/5. So if you look at the graph, we'll just put negative 3/5 here, wherever that is. We'll just say it's right there. So at that point, it is now discontinuous. So beyond that, beyond that, we don't have it's not in the domain, but at that point, we're discontinuous. All right, find all values of x where the piecewise function is discontinuous. So when you look at these, polynomial, polynomial, polynomial. So 5x minus 4, polynomial, x squared, polynomial, x plus 6, polynomial. So we're continuous. All those functions are continuous wherever they're defined. So less than 0, we're continuous. Between 0 and 3, we are continuous. And greater than 3, we are continuous. The only places we have to consider are, what about x equals 0? And we'll come over here. What about x equals 3? So let's see, what is the limit as x approaches 0 from the left? So when we're on the left of 0, we are less than 0. So we are looking at this function. So the limit as x approaches 0 from the left of 5x minus 4. This is a continuous function, so you can just plug in 0. You're going to get negative 4. Now, what about from the right? Limit as x approaches 0 from the right. So now when we're on the right, we are considering the x squared part of this function. So we're greater than 0 if we're coming from the right. And so we need to consider x squared. So that equals 0. And so these two are not equal. The two-sided limits are not equal. So the limit as x approaches 0 of f of x, the two-sided limit, does not exist. So not continuous or discontinuous at x equals 0. All right, now what about x equals 3? Let's do the same thing. So the limit from the left of f of x, so we're coming from the left, so we'll be less than 3, so we're using x squared. So the limit as x approaches 3 from the left of x squared, that would be 9. And then the limit as x approaches 3 from the right, now we are greater than 3, so we're going to be using the x plus 6. X plus 6. So x plus 6 is continuous. We can just plug in 3 and we get 9. So now these two are equal. So now the last part to consider, what is f of 3? Well, we're defined from x between 0 and 3, and we are including the endpoint. So f of 3 will be defined on x squared. Or I guess we should write 3 here. 3 squared, which would be 9. So we are continuous at x equals 3. Now, I think one of the homework problems, you're going to have to graph one of these. We'll graph this real quick just for the practice. But as far as going through deciding if this is continuous or not, look at each piece. And if it's not continuous, so if we had a root function here or a rational function, you would need to decide, is it continuous on this entire domain, however it's defined. So you don't have to check everything. But if it's defined on its whole domain, you can say it's continuous. And then you just need to check wherever it splits. So in 0 and 3 in this case. All right, so how do we graph these? Probably did these in Precalculus at some point. So let's draw. These are not asymptotes, but let's just draw borders here. So we have a border at 3 or at 0, and we have a border at 3. So not asymptotes. These are just borders. So 5x minus 4. So we have a y-intercept of 3. So we're going to have a hole here because it's just less than 0. And then a slope of 5. So it's going to look something like that. So there is our 5x minus 4. Then between 0 and 3, we go to, we're drawing x squared. So f of 0 would be 0. F of 3 would be 9. We'll just draw it up here and then connect that with the parabola shape. And then x plus 6, that's a slope of 1, positive 1, so it's going to go up like that. And we already know that if we plug in 3 here, we get 9, so that's continuous there. All right, so that's what the graph looks like. So we can see the jump discontinuity, and then we come up here and we can see that it's a corner, but it's not a smooth transition, but it is a transition. So it is continuous. All right, what about number 8? So we have the absolute value of x plus 1 over x plus 1. So now you might remember from doing rational functions, you need to simplify this before you figure out where the vertical asymptotes are. Now, there actually is not a vertical asymptote because this will simplify, but you got to be careful. So it's not just 1. What if x is less than 1? If x is less than 1, so let's just say x equals 0. What is f of 0? Well, we have the absolute value of 0 plus 1 over 0 plus 1. Actually, probably we should have said -1. Let's say -1. We'll do this. All right. Actually, let's make this greater than -1. That's where we should split it because that's where we get 0 on the bottom. Greater than -1. So let's pick 0. So here we get 1. Now, what if x is less than -1? Say x equals -2. Then f of -2, we get -2 plus 1 over -2 plus 1. So absolute value of -2 plus 1 is going to be 1. And then -2 plus 1 is -1. So f of -2 is -1. So these will always split. This simplifies to 1 or -1. And then it splits wherever this equals 0. So we have 1 or -1. If x is greater than -1, it's 1. If x is less than -1, then it's going to be -1. What if x equals -1? So if x equals -1, f is not defined. Because we get 0 on the bottom. And we get 0 on the top, too. So what does this graph look like? So -1 when we're less than -1. So it's going to come like this. Let me erase that. So we have a hole there. So less than -1 and then greater than -1. So there's our 1, there's our -1, -1. So linear function, and we have a jump and it comes up. So at x equals -1, we are not defined. And it doesn't matter what you have here. So even if it's f of x equals absolute value of 2x minus 7 over 2x minus 7, it still works the same way. You just got to figure out where this jump is, what the x value is. In that case, it'd be 3/2. All right, where is 3e to the 1 over x discontinuous? So e to the x is continuous everywhere. 1 over x is not, though. So 1 over x is discontinuous at x equals 0, because we cannot have 0 in the bottom. So this means, so this is continuous everywhere, but we don't have e to the x. We have e to the 1 over x. 1 over x is discontinuous at x equals 0, so e to the 1 over x is discontinuous, I won't write the whole thing, at x equals 0. And then, of course, 3e to the 1 over x is also discontinuous there. Okay. All right, and then last one. So we have a piecewise function. We have a rational function up here. Of course, this one's not defined at x minus 2. And it's not defined here, or it is defined this way when x is not equal to 2. But when x does equal 2, we're going to write it as kx minus 3. Now, we need to find the value of k so that these two are continuous. So we need to show... We need to basically get the limit as x approaches 2, and we'll be using 4x squared minus 5x minus 6 over x minus 2. So we need to find that, and then we also need to solve this equation. Well, we need f of 2 to equal that as well. So let's just write that up here. So f of 2 equals f of 2, which f of 2 would plug into right here. Okay, so now how are we going to get this? Because if we plug in 2, we get 0 on the bottom, and that doesn't work. So what are we going to do? Well, we could probably factor this, and probably a factor is x minus 2. So let's divide... Let's go back to college algebra or precalculus, and let's divide this and see how this works. So I don't readily see how to factor that. Probably could. I'm sure you can, but if you don't readily see how to factor it, but you know x minus 2 is a factor, then let's just divide. So we get 4x multiply, so 4x squared minus 8x. Then you subtract. So we get 3x minus 6, and x goes into 3x 3 times, so 4x plus 3. So this would factor, so 4x squared minus 5x minus 6 factors into 4x plus 3 is x minus 2. All right, so the limit as x approaches 2, 4x squared minus 5x minus 6 over x minus 2, that equals the limit as x approaches 2. This simplifies to just 4x plus 3. Because the top simplifies 4x plus 3 times x minus 2. The x minus 2's will cancel. Then we just plug in 2. So 4 times 2 plus 3, that gives us 11. Now, this limit equals f of 2. F of 2 is k times 2 minus 3, or we could write 2k minus 3. So now these two are equal. So the limit to the left-hand side is 11. The right-hand side, f of 2, is 2k minus 3. So now just solve this for k. So add 3, we get 14 equals 2k. So k equals 7. There you go. Okay, so the main thing to remember your definition. The limit as x approaches that value has to equal the value of the function at that point. And that's all we're doing here. All right, so that takes care of that, and we're going to move on to rates of change going forward, and we'll start to get into derivatives and some more interesting things.